have a question.
I also have question. Okay, your question first.
Okay, look at line 22.
Line 22.
22, yeah.
22. We are at line 60, Daniel.
Sorry.
Line 22. Okay. What about it?
You did mesh grid for TT, PP, and why do we have two different kinds of arrays?
Different kind of array. Why not?
I mean,
Does it matter? Do you have to match the number of points in X and okay, in another word, your picture, do you need a square? Do you need the same number of cells on the X direction and Y direction? Do we? The number of cells doesn't need to match. How many cells do you have on on X? We have 1, 2, 3, 4, 5, 6. Come from 7 points. On Y we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Come from 11 points. Which is perfectly fine. Initially when I created, I should have 7 points in temperature, 11 points in pressure. It doesn't need to match. That's the point.
yeah, I know that. But what I'm trying to say is that when we do mesh grid, you just like, okay, for each value of T, you assign a particular value of T to you. Or you have different arrays.
Okay. What is the shape of capital T? 1 capital T. What is the shape? 7 comma, right? What about P? 11 comma, right? What about TT and PP? God. TT will be type TT.shape. Type it. Did you type it, Daniel? TT.shape is 11 by 7. PP.shape is 11 by 7. In order to use P color, you use P color to do the plot, right? We need X value and Y value at every point. And you have how many points? You have 7 points on X, 7 column, 11 row. So the temperature mesh has to be 11 by 7. Pressure mesh has to be 11 by 7 too. But it has to cross each other so that at this point, like at this point, you use this point you use different temperature. Okay? It's just make the plot. If you cannot do it, we should talk more after class. You have the problem for the test, for the exam too.
This problem?
You will very likely to have some problem in the test, in my exam. It is better to help you before the exam, not after the exam.
So you said the last lecture, the exam will call out.
This thing, we did it already, my dear. We did it long time ago already.
Can you go through lines 66 and 67 again?
66 and 67. Line 66. I think my line 66 and my line 67 is defined a little bit different from you.
Okay, 63.
63. So that is step 3.
Okay.
So this thing, I just skip. You know the concept, you know the code, you can do it. For graduate student, of course.
Oh, this is the code.
This is the code for double interpolation. Okay, you can use what? Z predict 0. What's that? Z predict. You can use SciPy to do this, I think. Did I? I did. I do model equal to interpolate dot inter p2d. X is t in, y is p in, z is mu in. So this automatically do use to the interpolation, okay, and I get very close answer. I don't know why it's not identical, but I'm fine with that. So this is how I did it with automatic function, and I show you how to do it manually so that you understand the algorithm itself. Okay, let's do cubic spline. So for cubic spline, we want to connect 2 points with a curve, not a straight line. It should be better, right? So we do piecewise third order polynomial. Okay. And I give you the equation without any derivation. No derivation is given. Did I talk about that? No. You can look at the if you're from math department or you want to do something in detail, yes, we talk about the derivation. But let's talk about how do we use it first. Once you have equation. Okay, we have equation Q equal to 1 minus t, y1, t, y2, plus t, blah, 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 blah. T is scale x, x minus x1 divided by x2 minus x1. A is short for k1, x2 minus x1 minus y2 minus y1. B is blah, 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 blah. K is the slope. That's the point, okay? K is the slope. K1 is the slope at point 1. K2 is the slope at point 2. X1 is the x value at point 1. X2 is the x value at point 2. Same as Y. Y1 is the point value, y value at point 1. Y2 is the y value at point 2. Q is the function value. Okay. Once you do interpolation, that at the unknown x, that is the y target that you have. You have your x target, right? So this means if you do just 2 dots, simple cubic spline between 2 dots, what do we need? We need location. We need x1, we need x2, and we need y1 and we need y2. In addition to that, we need slope at point 1 and slope at point 2. Okay? That is the required given information. Next step, we need to know what is the x target. We want to calculate y value at x target, right? So I will have to tell you what is the x target. So x target is the point of interest. Once you know your x target should be between x1 and x2. You plug it in the equation to calculate t. Once you calculate t, you calculate a and b too. You can directly calculate a, right? Because k is known, x2 is known, x1 is known, y2, y1 is known. So you can calculate a and you can calculate b. Plug this t into this equation, then you can get y target. Wow, very nice, you see? Now you can do curve. Okay. One classic example is this. x1 equal to 0, y1 equal to 0. So we start at an origin. x2 equal to 1, y2 equal to 0. Okay. Slope at point 1 equal to 1, and slope at point 2 equal to 1. So you have 2 points and same slope. How do we connect it together with a smooth line that is differentiable? So I define everything, x1, x2, y1, y2, k1, k2, t, and q. I plot it. Wow! It gives me third-degree polynomial. So when you know the slope, you know the point, you can connect it with a smooth line, differentiable. So we check the slope at point 1 and point 2. I recheck the slope. It is 1 and it is 0. See t value and t value. What is t 33.3? My t is that slope? Basically what you get match to what you expect. Okay. If you have slope at origin equal to 1 and slope at point 1 equal to -1, it will give you parabola. Okay? It connects two points based on the point and the slope. That is cubic spline for 2 dots. What about, okay, check the slope by use numpy gradient. Okay, numpy gradient, just this is the documentation for numpy gradient. But I just tell you there's another way to check the slope by use numpy gradient. Put Q value and put T value in, you get the result. You can manually check the slope. Look at this. It's manually checking it, right? You get the value. Okay. Look at cell 76. Cell 76 is central scheme. Why do I say it like that? I have slope between point 65 and 66 and slope between 66 and 67. Then I average two values of the slope. That is more accurate. Okay? You have point 1, you have slope to the right hand side and slope to the left hand side. Average of the slope value give you second order scheme, which is more accurate. Alright. Basically, when we check the answer, we get what we want. Now, do cubic spline for several slope conditions. So that picture is generated by doing cubic spline. You see the blue one, orange, green, red, purple. Those are cubic splines. Okay? But it is done with the different initial conditions for the slope. So when I vary the slope, it connect those 2 points with a curve, which is a differentiable. Very good. What if we want to do full cubic spline interpolation for multiple points? You have many points. What you will get is piecewise continuous third order differentiable for between interval. You have several splines. Okay, if you have 2 points, you have 2 intervals. You have 2 functions. Okay? If you have 10 intervals, you get 10 functions as a result. The good thing is, okay, piecewise cubic equation will be used to connect the point. Property of the cubic spline output, Qx is piecewise continuous function. Q prime is piecewise continuous function. Slope is continuous. Okay? Q double prime is a piecewise continuous function. And Q double prime at the starting point and Q double prime at the end point equal to 0. There are several ways to do the cubic spline for many points. Notice that this time you don't need to know the slope. Isn't that good? For multiple points, you don't need to know the slope. You just need to know the point. And you have to, because you never know the slope, right? How can you know the slope? When you do the interpolation, you get the point, the data, x data, y data, but you don't know the slope at each point. So with that, we need 2 boundary conditions at the beginning and at the end, which is Q double prime. We can set Q double prime to be anything, but with different Q double prime, you have to rewrite your equation. So I show you just one, which is natural boundary condition Q double prime equal to 0. What is Q double prime equal to 0? Q double prime, second derivative of Q with respect to x equal to 0. What does it mean?
Means that equals
Slope was constant.
Constant slope. So this means at the end your line doesn't twist. Okay? And if you extrapolate it, it's straight. That's the part. Okay? q double prime equal to 0, this means q prime on the slope equal to constant. Constant slope is linear line, right? That's the assumption for natural boundary condition. But you can have the twist boundary condition, but you have to redo the whole derivation for the equation. Okay. Calculation step is this. Specify x and y for each point for the known point. Calculate the slope at each point by using cubic spline. Okay. Create equation of each interval from the obtained slope. Then use the equation from step 2 to do interpolation. So basically, cubic spline interpolation gives you the slope at every point. Once you know slope at every point, you can use previous method, right? This method to create a line between those 2 points. Once you know the slope. But the point is, how do we get the slope of every point? Okay. There's an automatic function. Just click and it runs cubic spline. But this is for you to understand the algorithm. Okay. I generated. Did I explain them here? So, cubic spline. Curve example. Oh, okay. Let's do this. Let's take a look at it first. Before cubic spline interpolation, I have several dots. Okay. With cubic spline, it connects the dot without knowing the function. The function is generated from, I think, function sign, like tilted sign with the slope. But this, look at this, how close? It's very close.
Okay.
Do you like it?
What's the difference between this one and regression? Because the
Regression
is
gives you
the same-
one straight line,
No,
pass to the middle. If you, okay, linear regression. If you have several dots like this, you do linear regression, you get one line. If you do like 8 order, 9 order regression that pass through every point, it's not the same in the sense that for regression, high order polynomial regression, you get one function. But this one, you have the number of functions equal to the number of intervals. Okay. And it doesn't use information that is like far away to calculate the curve. It used but okay, how many curves I have? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If you fit with polynomial degree 15, you will probably get something like that.
yeah, something like that. And you already have your test data, so
Cubic spline give you the slope too. It gives you the slope at every point. It's different method. Okay, one of them is to just interpolate. Okay, it doesn't do any prediction. And I think there is a difference. If you remember, maybe it's not a difference. I have to check. But for cubic spline, it can do similar thing for polynomial degree 15. Okay, analytical slope value, C-spline value, very close. Integration, does it do integration? Okay, cubic spline slope calculation, how do we do it? Basically, we have a bunch of equations and we have to solve it by use system of linear equation. That's how we get the slope of each point. From Wikipedia, for natural boundary condition, which is q double prime equal to 0, we have this equation. Equation number 1, equation number 2, equation number 3. And definition of xi, vi, ci, di. So basically we can write system of equation into this format. The promise is this: if you solve this function without knowing how to derive each of them, you will get the slope at each point. That's the promise. The derivation for the equation to be used is skipped. We don't do derivation. Okay? But the idea is there's the equation. There are many equations. The number of equations equal to the number of points. Okay? And we have k0, k1, k2, slope at every point, n point. N plus 1 point, okay? Slope at n plus 1 point. And we have the equation to solve. It's a system of linear equations. So let's take a look at the equation for the top one and the bottom one, which is for the end point, is not the same as the equation for the middle one. That's why I use B and C, okay? Let's take a look. What is that B and C? So basically from Wikipedia, you have these three equations, an equation for the endpoint. Then rearrange it. We can rearrange it AI equal to that, which is just one number. It's a scalar value. BI equal to that, CI equal to that, DI equal to that. What do we need to calculate AI, BI, CI, DI? Martina? So how do I calculate AI, BI, CI, DI? What do I need to know? Just do I need to know the slope? Just x and y, right?
Yes, sir.
So just the position. Okay. And that's it. Once I calculate AI, BI, DI, CI, I put it into tridiagonal matrix form. I solve it with Thomas algorithm. Or you can use Gaussian elimination or array decomposition, whatever you want. Then you get every k in the code format. Okay, I have B0, C0, D0, AI, BI, CI, DI. Notice that I did not define it with the same equation. So B0 and BI is not quite the same, you see. I define it separately. For B0, where did I define it? Maybe that's from Wikipedia. Okay. B0, equation for B0 is not given, I didn't type it, but it is that. Okay. Equation for Z0 is that. X1, X0, Xi, Yi, so it's like different point from vector X and different point from vector Y. So the idea here is we skip all the derivation, but what we know is there's a equation for each part, for the system of cubic spline. We need the number of equations to match the number of unknown. The unknown is the slope. So we use a formula in Wikipedia. We can get the coefficient matrix, every location, and then use Thomas algorithm to solve it. Daniel, what is Thomas algorithm?
Is a method of solving a system of linear equations.
Is there any specific requirement for Thomas algorithm? What is the requirement? Can it use for dense matrix? Can it use for sparse matrix? It must be 3 lines in the middle. Okay? 3 lines in the middle. Then it works. If it is not 3 lines in the middle, it doesn't work. So that's the code. Once solve it, or you can do model equal to scipy.interpolate.cubic spline. Okay. And boundary condition type BC underscore type equal to natural. Okay. And then to predict, y predict equal to model parentheses whatever vector that you want to predict. So this means it predicts y value at every point that we input in. So manual method match with SciPy, then I'm done. I did it right. But do you? You don't need to do it, right? You just use mine, it's the same. Calculate slope integrating area from cubic spline. For integrating area from cubic spline, think about it. You have cubic equation, right? Cubic spline is cubic equation. For cubic equation is, maybe that's one of the benefits. You connect it with cubic equation, it's easier to integrate. If you connect everything with degree 15, when you integrate it, it's kind of expensive. But if you connect it with just cubic equation, it's cheaper. So to integrate it,
What is
model.integrate, just that. That is integration. Done. Model.integrate.
So why is it called cubic spline?
Because how do you connect them together? Let's take a look. How do we connect them together? We use t multiplied by t multiplied by t. Cubic equation. Yes. Cubic equation of normalized x. Because we use cubic equation, we call cubic spline. I got a notebook. So I generate the solution by use sine function plus x. Okay, so it's at a little bit angle. So, and then I extract some point and use that point to do cubic spline. So I have equation for B, A, B, C, do tridiagonal matrix, and AI is this, and you actually need the equation for the endpoint. Equation for the endpoint. Once you have everything, I use sparse dot diax, that is to generate tridiagonal matrix quick. If you don't do sparse, that's slow, okay? So if you do sparse dot diax, that is the way you can generate tridiagonal matrix quickly. We talked about it already. So it can be in the exam. Equation for B0, C0, D0 is here, and for A and B and Dn is here. I didn't type it, but it is here. So once you do everything, you rearrange it, put it in diagonal format, and then you do sparse. Diag is B, B, A, A, C, C, and put the offset, and then you're done. Then you solve it. Okay. You can use scipy.sparse.linear-algebra.sparse solve. Okay, but it accepts CSC type. So you do .csc first. Comma dd is the right hand side. Okay. Step 2 plus step 3. Use simple cubic function to generate the interpolation line. We already have the function, right? You see this simple cubic. What is that simple cubic?
1 minute.
Yes.
What is this CSC?
CSC.
CSC.
Is that column something? I remember we talked about that. CSC. What is CSC? It doesn't tell the full form. One of them is column, one of them is row. Column separated, row separated, something. We talked about that. Maybe I'm wrong, but 2 weeks ago I'm right. Okay. So it's a method to store sparse matrix efficiently. Okay. If you recall, you have the pointer variable to tell how to split the data or something. But we don't really go into detail, but you just know that there are two types. And you can change the type between diag and CSC by that. Okay. So simple cubic. Simple cubic is the function that here, look. is user-defined function. Simple cubic require x, which is the target x, x1, x2, y1, y2, k1, k2, and it produces target y. So this is my own function, right? So basically, I solve system of linear equation. I get the slope. I put the slope value back into user-defined function, which is simple cubic. Then I can generate point, many point. So simple cubic, I did not put just one point. I put vector in, then I get vector out. This is the beauty of Python. If you write C++, you have to do like operator overloading or something, but this time, whatever you put in, it adjusts automatically. If you put in single value, it outputs single value. If you put array in, it do element by element calculation, and it give you the correct answer. So I calculate cubic spline for every range. So every range, that's why I use for loop. Every section. Then I plot it. Okay. Point generated function, cubic spline answer, given point. So it close to the true solution. If you use just SciPy, maybe it's quicker. Of course it's quicker, but you know the concept from here. What is in SciPy? But this is not exactly what's in SciPy, okay? SciPy use either C or Fortran library, which is faster. Okay? This is just to show you the concept. What is inside? What do we have to do? Cubic spline. Integration from cubic spline. Value and slope. Look at the slope. Slope value is still continuous, right? You see that? And second order derivative is it's continuous, but this time it's not differentiable. It's like a spike up down. Okay. Yes.
The original function was a sine function. I mean, for
SciPy function?
no, I mean the blue line was it sine function.
I don't know. The blue line is prediction from cubic spline. Once I know the slope, I put the slope into that two-point method, and then I can generate everywhere. Okay. So the two-point method that you see, we actually use. What is the two-point method? This two-point method, you understand that, right? So then you, for multiple point, you generate a slope and put the slope into that two-point method. Then you can get the value for every interval, and then you do that for every interval. Done. What's this part? Relative error. Histogram of error. Analytical solution. Do we have? Okay, where's the side part? It's very close. Oh, okay. Now I use SymPy to do the integration of my function. I can integrate it by hand too, but okay. Why not? Why don't we use SymPy? SymPy can integrate it automatically. So SymPy.integrate and put the equation inside. Then it gives me the integration result. I evaluate it, I get 11 something. This is symbolic calculation, symbolic integration of the original is analytical solution for the integration. Look at this. Integrating the cubic spline, you get the blue one. Analytical solution of the function that used to generate everything, you get the orange. They match. Very close. So integrating from cubic spline gives you the same result that you integrate from original function. Isn't that good? So if you have some complicated function, one of the methods is to, okay, how do I integrate it? Integration is our next topic, but how do I integrate it? Integrating. Oh, I use model.integrate. Just that. I use scipy function to do the integration. 16, 4 more minutes. Okay, what we do? For this 4 more minutes, we can do a little bit of integration, which is trapezoidal method. How about trapezoidal method? Okay, trapezoidal method. Next slide. Integration, most of the time, cannot be done analytically. Differentiation can be done analytically, okay, but not integration. Okay. So integration is not every time that you can do it analytically. We have several topics. So second order accuracy, we can use trapezoidal. Simpson method give you better accuracy. Okay. For trapezoidal method, conceptually you have the line, right? That is the line. Function that we try to integrate. For trapezoidal, you create trapezoidal shape. So connect it. First step, you discretize it, right? And you connect with the line. And then you calculate the value of trapezoidal shape. Trapezoidal shape has the formula of what? 0.5 multiplied by the summation of the height, the parallel height, multiplied by the gap, right? So FA plus FB is the summation of the parallel line. So you have two lines in parallel. And multiplied by 0.5 and multiplied by gap. Gap is A minus B. So this means you get one of the section. You do it again, you get another section. You do it again, you get another section. Add all that together, you get integration result. Look at this. You can see it doesn't match, does it? You connect 2 points with a straight line, but original equation is curved. It won't match. How do we get a better result? You discretize more. What if you don't want to discretize more? You can use the same number of points, but when your function change quick, you discretize more. When your function change slow, you discretize less. That's another trick. So trapezoidal method is still better than Riemann sum. Riemann sum, you just have a bar and add the bar value together, right? This time we connect the top part with a straight line. Okay. Look at this one. Interestingly, I use number of nodes equal to 12 and also equal to 12. But my function looks like this, okay? When function change quick, I do more discretization. I put more node over there. When my function change slow, I put less node over there. And it is a lot more accurate. Wow. You don't have it? Very nice, look at this. It's a lot more accurate, even though both of them use 12 points. It is matter on the number of points, okay? Let's say if 1 point, calculate function value take you like 0.1 microsecond. That doesn't matter. But what if 1 point give you 1 day? Let's say you do the experiment in the lab. 1 point give you 1 day. Okay? So you don't want many points, right? But what if you want to integrate it correctly? You have to select the right point. Where the phenomena change quick, you do more tests. Where the phenomena doesn't change much, you do less tests. That's the idea, okay? Redistribute it so that we get more accurate result. Next one will be Simpson method. Simpson method is the 4th order, okay? Trapezoidal is the 2nd order. And later on we can do double integration. Do you want to do that? Double integration. And we have an automatic function with scipy, and I also show you how I did it manually. It's a little bit complicated, but it's fine. Okay, see you next Monday. Next Monday we will be in 204, and we have another professor to audit the class. Okay. That's it. Thank you for coming. For those of you Who need help from me? Okay, we will talk more for homework. Bye bye.